Yeah, you can see.
Okay, better like this. So we are all online, or should we wait a couple of minutes more? Maybe we can wait 2 minutes. 5, okay, it's 5 minutes past 2, we will start. Okay. So I guess we are more or less all online now, checking the numbers. So I think if you have nothing against it, I would start. Okay, so if you remember last time, we started discussing how to estimate the site response. And we were distinguishing, I go back of one slide, about methods which are based on a reference site or methods which are based on the usage of recordings without a reference site. In this particular, when we are dealing with a reference site, the typical and most used method is probably the standard spectral ratio method, where the spectral ratio between the same ground motion, I mean the same component of ground motion, so it can be in general the east-west or the north-south, or a combination of the two horizontal components that we are recording with a station, at a certain particular site is divided for the spectra of the same component or the same combination at a reference site. This is generally done when we have two nearby stations. In the case we don't have nearby stations, then we have to use a different technique that is producing a similar results, but decomposing, let's say, the spectra through an inversion. And this allows us also to obtain a site response, for example, for stations which are relatively far away or large seismic networks. So we mentioned last time that if we have an earthquake, let's try to show it with a pointer. If we have an earthquake in this area, it can be recorded by two stations. One, let's say above soil layers, for which we would like to estimate the effect, which are our site effects, and one at a rock site. And the two stations are quite close. If you remember from last time, the seismogram that we are recording is just a convolution of a source function for the propagation and for the site response. So just the convolution of this three terms. And we also said from the very first lecture that if we take the Fourier spectrum of this function in the time domain, it means the spectrum of the seismogram will be the product of the spectrum of the Fourier transform of the source function, of the propagation, and of the site. So we can describe this as a simple product of the spectra. If we take the modulus of each spectrum, then we know that what we are recording on soil, this is the spectrum on soil, and this is the spectrum on rock, will be just the product of the spectrum of a source at the path and the one corresponding to the site. So since we are assuming that this earthquake is enough far away from the two stations, so the interstation distance is relatively small with respect the hypocentral distance, we can assume that the propagation and the source are nearly the same for the two stations. So when we take the spectral ratio between the recording on the soil and the recording on rock, we are canceling the two source term because the stations see the source in the same way. We are also canceling the two terms related to the propagation. And since our rock site is a reference, so we can put it equal to 1, what remain is directly the response of the site on soil. So the effect of the propagation in these shallow geological layers. So if we go a little bit more operative, and now we will make also a small exercise. I will try also directly with recordings. So generally what we have two recordings of the same earthquake at two different stations. The blue one is the station on rock, and the red one is the station on soil. You see that immediately the two recordings are quite different, both in amplitude and in duration. These are real recordings that we took for an experiment in the basin of Gubbio. The component of shaking is the same. In this case, I'm using the horizontal component and in particular the component for the recording that is oriented in the north-south direction. Then what I'm doing, I just select a window of signal. I take this window of signal starting from the shear waves because we are mainly interested in the amplification of shear waves. And I calculate the Fourier transform that you see here in red and in blue for the reference site. Then I can make some smoothing of the spectra. So I just avoid to have this very large oscillation in the spectrum. I just regularize it a little bit. And from this, I take the spectral ratio. From this spectral ratio, I assume that the source component is removed, that the path component is removed. So the results of the spectral ratio that you see here in green should correspond to the site response at the station that you had here in red. This operation then is repeated for the different components in this case, but especially for many earthquakes. And what we are doing, we just average the results that we obtain from many spectral ratio. So here you see in red and in green, the results for the north-south and east-west component at the station that is reported here on the top. So you see in this case, the two components are showing similar amplification in the two directions of shaking, so the north-south and the east-west. But what is really striking, if you remember from the previous lectures, this site response when we only consider the vertical propagation of waves, and especially of SH waves, what we observe here is that, okay, we have a sort of first peak that corresponds to the resonance frequency of the site. In this case, at quite low frequency, we are at 0.35 hertz nearly, but then a very large amplification up to a factor 10, covering a wide frequency range, I would say up to 10 hertz. So we have a very wide band with very large amplification. In this case, this is due to the fact that we are in a valley where not only we have amplification due to the vertical incidence and resonance of the shear waves, but also because we have, if you remember, 2D or 3D effects. So we have also diffraction of waves at the edge of a basin that are generating also Rayleigh waves that we observe here that are strongly amplified in the basin itself, Rayleigh or Love waves. So the method in this way is quite simple. We just need a station in our site, a station in what we can consider a reference site. Then we have to wait for having a sufficient number of recordings. For each recording, we calculate the spectrum on certain windows of signal, and then we can estimate the site response through the spectral ratio. Okay, this is for an example of the application of this method in the valley of Gubbio that if you remember, we showed it already the first time when I tried to convince you that due to the single earthquake, there was a very large difference of shaking over a small distance. So here you see reported all the stations along a profile cutting the valley. The first station that we indicate as 0 is the station that we know it is on a hard rock site and that we will consider as a reference station. And then you have several stations, 9 at least, that are 8 stations from 1 to 9 inside the valley and crossing the valley, so recording the shaking inside the valley. And the station number 10 that is expected to be like a sort of other rock site station. So we recorded many events. And for each event, we have done exactly what I was discussing before. So we select the windows of signal, we calculate the Fourier transform, and we calculate the ratio between each one of these stations from 10 to 1 with respect to the station 0. And we can also do it for many earthquakes, and we took the average. The band in gray that you observe here generally are the standard deviation, while the red and the green curve are the median of all these calculations for different earthquakes. So what we observe is that already at station 1, there is some amplification of a shaking, mainly around 1 hertz, and then some more or some larger amplification in the high frequency range. This we could explain it considering that station 1 is nearby the edge of the valley where we expect that the sediment cover thickness is relatively small. Then we enter in the valley, you see station 2, 3, 4, and so on. And you see immediately that we have resonance frequencies, which are becoming lower and lower. For example, at station 05 and 07, which are more in the center of a valley, they go down to 0.3 hertz. But also what is striking is that there is a very large frequency band, which is amplified or shaking. So it means the stations here have a strong amplification, not only the fundamental resonance frequency as we expect, but also over a very wide frequency band. At station 9 and 8, we see that the resonance frequencies start to increase again because we go to the edge of a valley again. Surprisingly, at station 10, which we were expected to be on rock again, we still observe that we have some amplification, especially in the high frequency. This was quite an interesting result because I would have expected, being in the field, the station 10 and station 0 could both be good reference site. So in this case, I would have been mistaken because station 10 shows some amplification, also significant, with respect to the very hard rock site that is by the other side of the valley. So we learn.
Professor,
Yes.
can you come back to the previous slide?
Yes.
We can see to the station. Okay. The station 0 here is not recorded.
Yes, it is recorded, but it's the one that I use as a reference in the spectral ratio. So this is the spectral ratio. If you go back, this could be stations 0, for example. And this is the station 8, okay?
Okay.
I calculate the spectrum for both and I take the ratio, which is the green. So the ratio is valid for station 8, okay? So if I would calculate, of course, station 0 divided station 0, I would have 1. So it's divided itself,
yes,
okay?
Yes. Yeah.
Obviously. Okay, so there are two important things that we learn from here. And first, that the method to be valid, in general, we know we have to assume that the source is seen in the same way and that the path is enough long with respect to the stations, interstation distance. And generally, this is reasonable if we assume that the two stations have a distance 5 times smaller than the hypocentral distance. In this order is a rule of thumb, just to give you an idea. The other important point is that, okay, this method, we knew it then, can be only used if there is a good reference site nearby my site where I want to study site amplification. And in many cases can also happen that I don't have a rock site or a very good rock site close to my area where I want to study this. But if we look also to the results for station number 10, we are learning something a little bit more. What we define a rock site sometimes might not be a good reference site. So in that case, also what is reasonably rock can have its own site response, maybe due to weathering, fracturing of the rock near the surface and so on, but so has its own site response. And therefore, the selection also of a good reference site might be not so easy and should be done with a certain care. Okay. So before, just to make it a little bit more clear, the procedure, I will try to share now my screen with another window. Okay, this might be a bit tricky in this way. I try. Okay, now you should see my whole screen, I guess. Can you see it?
Yes.
Okay, so now I just run a small computer code just to make a sort of a example. So just imagine the case of before. We want to have the recording of the station in a central area. So copy. Ah. Okay, GU. So I'm loading now in my small code just a recording, which is taken exactly from the valley you have seen before. So this is for the station number 7. And I will take not the east-west component of shaking, for example. And now I will do the same for station 0, 0. You remember the one that was considered as a reference. And exactly for the same east-west component. And here the code is asking me how I want to smooth the spectra. You remember to remove this large oscillation due to the Fourier transform. So I just select a factor 20, which is giving me a reasonable smoothing. Okay, these are the seismograms, where you immediately see that the same component on the rock side, you see this is the blue one, with respect to what I'm recording in the middle of a valley, even if the distance is very short, they are very different. Okay, if I want to calculate the site response, so this earthquake I know from my bulletin, from my seismological network that is quite far away with respect to my station. So I know that this is a good rock site. I can estimate the site response at this site simply calculating its Fourier transform, the Fourier transform of this, and taking the ratio. So now I'm selecting a window of signal. So the selection can be trivial maybe, but it's not. Because I can select, for example, a relatively long window of signal. Oh. Okay. So I selected, you see in green here, a quite long window of signal. And in this case, the red curve is the spectrum of the seismogram above, but I don't know why it disappeared, but it's the seismogram above, below. And the blue curve is the spectrum of the seismogram below. You see immediately that there is a large amplification, and this large amplification, it's indicated here. And especially this large amplification is already affecting the low frequency range. So to go to this low frequency range, I had to include a very long window of signal. Do you remember why? So if I want to go to 0.1 hertz, I have to use a very long window of signal that is not only including the shear waves, but as you see, is including a very large part of a seismogram. Why I had to do this? If I was selecting a small window here around only the S waves, would I have had such a detail in my spectrum?
No, you will not respect the condition for the sampling. So
Exactly.
you will lose information.
Exactly, because the minimum frequency that I have in my FFT, it's equal to 1 divided the length of the window, okay? So longer is the window, I will be able to go to lower frequencies. So if I redo the same, so in this case, I can have a very good resolution. I can recalculate everything. Sorry, it's a bit slow. Now I will select a smaller window, for example. Okay. And now you see immediately the effect. I selected much shorter windows than before. And you can see that the spectrum, if we compare it, try to show it to you. Okay, you should be able to see it here. Okay, you see that in the right part, you have, you can go to lower frequency. We are more detailed in the spectrum. And this is also observing the spectral ratio. In this case, below 1 Hertz, I have a very poor resolution. So I just stop nearly here, and then I miss the information on this part of the spectrum. So why this is important? Because by one side, we would like to have the information about the amplification of shear waves. But to have information mainly only on the shear waves, we should take a window signal, like in this case, relatively small, and avoiding all the secondary phases. But if we do this, the window is too short to provide us information also relevant to the resonance frequency, because in this case, the resonance frequency is quite a low frequency. If we want to go to this low frequency, we have to extend the window signal like we have done here. So we take a much longer part of signal. What is the drawback that we have to pay? That the amplification that we will estimate will not be anymore only the amplification due to the effect of the sediments on the shear waves, but it's also due to the effect related to secondary phases coming later, like surface waves. Okay? So the point is always, when we are working in this field, we have to pay some compromise between what we can resolve with a Fourier transform due to the length of the signal, and how, let's say, precise we are in defining the amplification of S waves. So we risk to include more effect in our estimation. This is not a problem as long as we know what we are doing. So we know that if we are using a long windows, we will not focus only on the amplification of shear waves, but we will focus on the all amplifications effect that this site where we are analyzing is suffering. Okay? Is it clear, this?
Professor.
Yes.
When you compare the two images, I didn't see where I see it's almost the same. Can you repeat?
What is the same? The recordings are the same, but the spectra are different. Don't you see it?
Okay,
so
okay.
Especially in the low frequency part, we are losing this part of information. You can also go more extreme, if you like.
My question is the red plot, the red curve. What it represents? Not the red, the green one.
It's the ratio.
Okay, okay.
You see, now I make it even smaller. You see this small green line here? Yeah. It's very short on the S waves. Try to compare it to figure 1, for example, where we had the longest windows. Okay? You see immediately, okay, now you see that we have no information anymore in the low frequency. Okay. So all whatever it's happening below 1 Hertz, we nearly don't see it, no? This part here, it's only as a sort of average. And we cannot estimate at 0.3 where we have the fundamental resonance frequency. So that's what I meant. Here we are closer to the S wave phase, but we don't have enough resolution to see the resonance frequency of S waves because it's a lower frequency than what we can see. If then we try to solve a problem enlarging the window, of course we can have a site response which is more broadband, but we are not only considering the effect on the S waves, but we are considering the effect on the overall signal of the all phases arriving also later. So this is the compromise that we are always paying, let's say in this case. Is it clear now?
Yeah, thank you.
Okay. So now I go, yes?
Just a quick question. What are you using for smoothing? It's like a...
Here I'm using a Konomachi window. So it's a sort of, let's say, Henning window. So it's just smoothing regularly in the logarithmic scale, which is generally considered more appropriated, especially when your spectrum is spanning different decades. So give you a same amount of smoothing in the log domain. Okay?
Okay, thanks.
Okay, I go back now to the lectures. And now we load it again. And we share the screen. So Anna Maria, I would suggest you to use it, this kind of windows in your case. The only problem is that generates quite slow in the computation. So let's say with respect to other windows, but also in the ESP model manual is generally suggested to use a smoothing of the spectra using a constant in the log scale. So this would be preferable.
Yeah, I was actually using Konomachi, but
Okay.
yeah, I was curious. Thanks.
In this case, I use a 20 factor, which is a compromise from between large smoothing and avoiding too much large jumps in the spectrum. Okay, till now we saw the simple case, but just now imagine that we have a sparse network. And for each earthquake, so the stations are far away. My next rock station is at 30, 40 kilometers at least. But still I want to calculate, and one of a station of a network, what is site response. Of course, in this case, the assumption that the path is the same, that the source is seen in the same way by all the distributed stations is not valid anymore. So I have to try from the recording, from my data, to separate the contribution of each one of these terms, which are the path, the source, and the site response that are together generating the seismogram or the spectrum of the seismogram. This is generally done through a method that is called generalized inversion technique. And if you think to the source, to the path, and to the source, we said that the spectrum are simply a multiplication of them. If you take the logarithm of your observation, you can write that the logarithm of your data in the spectrum is equal to the sum of the logarithm of the spectrum of a source, the logarithm of the spectrum of a path, the logarithm of the spectrum of a site response. So we have a simple linear system. So if here we focus only on the attenuation term and the source term, we avoid only to consider, let's say, site effects, or we consider that the term M is including the source and the site. D of E is our seismogram, or better, is the Fourier spectrum of a seismogram that I record at a certain distance, which is the multiplication of this term that is including source and site for the attenuation function, so the function that is describing my propagation. You remember last time I showed you how this was looking like in the time domain and in the frequency domain. So if I take the logarithm of this datum, this will be equal to the logarithm of m plus the logarithm of a of m. So it's simple linear equation. So for each earthquake, I will have many recordings. How many? So depends on how many stations of my networks will record the first event. And I will have also many earthquakes. So I can write this equation for all the recordings of each earthquake and then for all the earthquakes. So I will have a number of data of my observation that corresponds to the number of all observations that I have. And just imagine this is a spectrum. So I just using only one frequency. I just make this calculation, for example, for only the frequency of 1 Hertz as an example. So this equation can be written in a matrix form where my data are the spectrum at one frequency, for example, of all the recordings. I will have a matrix A where I have a certain number of columns. The number of columns can be, okay, let's say I have a range of distance of recordings from 0 to 100 kilometers. If I look to the minimum distance in my data set to the maximum. And I decide to divide this distance in bins of 10 kilometers. So if my recording from earthquake number 1 to station number 1 is in the range of 6 kilometers, then I will put it in the first column. If it will be at 12 kilometers, since my bins have steps of 10 kilometers, will go in the second column, and so on. Then I look at the recording of earthquakes number 2, and I will do the same. So I will have a system with a matrix, with my data. I have to solve this system to obtain the unknown. Unknown are the attenuation for each bin of distance and the source term, source plus, let's say, side effects, if there is side effects at the station of the recording. So I can separate these two terms. Once I have these terms that was M before, I can calculate, I can correct my datum, the original one, for the attenuation. And I can say, okay, this residual that I obtain, again, can be decomposed in a terms corresponding to the source and the term corresponding to the site. Again, this is a linear system where my data are the residual for each single spectrum. And again, I will have a matrix where I will have a number of columns that correspond to the number of earthquakes, so our source, plus the number of sites or stations recording the event. So for the first earthquake, the earthquake number 1, recorded at station number 1, what I will have? I will have the first column of a source with a 1, all the others will be 0, and then I will have a 1 at the station 1. Then I will have always the source, the first earthquake, that is recorded at the second station. So in my matrix, I will have a 1 in the position corresponding to the first event, and the 1 in correspondence of the third site. Then the first event is recorded at station number 3. So I will have again a 1 in the position of the first event, and this time a 1 in the position of the station number 3. After some time, we start looking at the recordings of a second event. And the second event will be recorded at station number 1. So again, In this case, I will have a 1 in the second column corresponding to the second event, and a 1 in the station corresponding, in the column, sorry, corresponding to the first site, and so on. Again, I have a linear system with a matrix, which is a combination of 1 and zeros, depending on which station and which source was corresponding to the recording. And my unknown will be the spectral amplitude at that frequency for the source and for the site. So using this method, we are able to start from the original spectra, from the recordings, and separate the different contribution of a path, of a source, and of course, our main interest here of the side effects. So again, trying to go a little bit back, this is just one station that is recording many events. This is our matrix, these are the data like we had before. So when the station, this station is recording the earthquake at number 8, this earthquake number 8 is recorded at 46 kilometers. So since I have beams, in this case, from 0 to 50 kilometers, this is what I decide. With a width of 5 kilometers, the one will be located in this last column that is corresponding to 45 to 50 kilometers. When the station is recording the earthquake number 1, which is at a distance of 22 kilometers, which column will be filled? The column that is corresponding to the distance between 20 and 25, okay? If we turn it a little bit back, this is all the part of a matrix for station 1. And these are for station 1, the beams for the distance and the different earthquakes. Just imagine we are recording 15 earthquakes in this case, and there is a certain number of beams for distance, like 1, 2, 3, 4, 5, 6, 7, 8, nearly 10 for the distance. So when the station now is recording the event, station 2, at 3 kilometers, you see this is the second station, which beam will be filled? Okay, the first beam, because it's the beam between 0 and 5 kilometers. If this station is then recording the event number 3, which is much more far away, at a distance of 46 kilometers, this is always the second station. You see, this is the column for event number 3. And therefore, this will be the column for the distance range 46 kilometers, because it's the 10 beam is between 45 and 50 kilometers. So it's a sort of game where you fill your matrix depending on the combination of number of earthquakes and number and the value of the distance. And solving this system, you can split the contribution of a source, of path, and of site response. So this is an example of application in Turkey after the Izmit earthquake. It was a large example where we wanted to study, you see the site effects at all the stations of a network. But as you see from the figure, are more than 100 kilometers also far away. So of course, a single standard spectral ratio using these black dots that are the earthquakes would not have been possible. So we select one station as a reference station on rock. And then in this case, to calculate the site response, we had to use this generalized inversion technique. So we had to separate the contribution of a path, of a source, and of a site. So if you do this, you can combine many recordings. In this case, we use 262 events. And you see we have nearly 20 stations. We were considering a distance range between 8 to 145 kilometers. So quite a large distance range between event and stations. And this is the distribution of stations. So we knew that most of the event anyway were at distance smaller than 80 kilometers from the stations. And this was the range of magnitude 0.5 to 4.2 that we have been considering. So these are some examples of the results of a site response at many of the stations of these, at 4 of the stations of a network. You see that depending on the position, so this is 3, 4, 8, and 14. So if you go back here, this is station 3, this is station 4, this is station 8, and this is station 14. So you see also stations quite far away. You see that these stations can have quite a different site response. Station 3 has a very, let's say, large amplification, mainly around 4 Hertz, with a clear peak. Station 4 has a moderate amplification, quite small, but only in the very high frequency range, so 9 to 10 Hertz. Station 8 has a little bit more complicated site amplification with a lower frequency peak around 2.5 Hertz, and then a high frequency peak at 10. And station 14 had a more broadband amplification with a maximum around 1.5 Hertz, and the second, let's say, near the peak around 3-4 Hertz, and then decaying and becoming even smaller than 1 at frequencies larger than 10 Hertz. So these stations were showing quite different results. The uncertainties in this case was estimated using what is called bootstrap method. So it means we repeated the inversion, removing one datum in a random way and substituting it again in a random way and repeating the inversion and checking how much the results changed and so on for a large amount of time. And this gives you the stability, let's say, of the solution that we obtain. And as you see, it's quite reasonable, good. The same method can also be applied in even complicated situations. This was, for example, the case of Vrancea area in Romania, where earthquakes are generally quite deep, can be very large, with large magnitude, even up to 7, but with depth larger than 70 kilometers. And we also knew that depending on the propagation, the attenuation function could be completely different depending on the path. So we had to make some variation in this calculation. We had to consider 2 different attenuation functions in our matrix, one for the nearly vertical propagation and one for the propagation more far away. So whatever was recorded on stations nearly on the vertical of the cluster had the attenuation completely different from stations far away. In this way, we had to use 2 attenuation functions for the recording, depending if it was propagating through one region or the other. And this was also shown as the results here, where we had the different attenuations for different paths, and so on. So this is the method that we generally use when we are using spectral ratio. Of course, there is another example of spectral ratio that is the one that you can calculate considering the recording at the surface, and if you have a borel, the recording in the borel if the station is on the hard rock. Intuitively, one would say, okay, that's a quite good situation, because if I have a recording on the top, I have a recording on the bottom. If I calculate my two Fourier spectra, I can calculate the spectral ratio, and immediately I have my transfer function from the bottom to the top. Okay? Our rock site is already, our input is already measured by the shaking coming from below. But as you see here, when we have a wave arriving, you see, due to the layering, we have a refraction and reflection. So I just imagine also simply to the surface, there is a reflected wave going down and affecting also the recording in the bottom. Just imagine to have a station here. So what we are recording in the underground, it's not only depending, like we already discussed when we calculate the theoretical 1D transfer function, it does not depend only on the input from below, but it's also recording, we will see it again, it's also recording the reflection of the waves you see already here, and this will become more clear here, the reflection from the top, from the surface. So we have also downgoing waves in the recording in the underground. So this means that a standard spectral ratio using the surface station to the downhole station might be not describing directly the transfer function from the bottom to the top. Okay? So generally, how is this done? This is done not only working in the frequency domain, but also visualizing this upgoing and downgoing propagation of waves also in the time domain. The first operation, again, is to calculate the Fourier spectrum of the recording at the bottom, the Fourier spectrum of the recording at the surface, and then making what we call the convolution. So here it's like the spectral ratio, but instead of working only on the Fourier amplitude spectrum, we are working in the complex domain. So we use the complex Fourier transform and we divide it for the complex Fourier transform on the bottom. Generally, we need some regularization. So generally, we use some term that is also providing a sort of stability, let's say, in your deconvolution to avoid that the denominator here is becoming too small, and therefore that we have some numerical artifact, let's say, in the resulting Fourier spectrum. So this is the Fourier spectrum of the spectral ratio, but it's complex. So to have the equivalent of what we have seen before, we should calculate the modulus. If then you take this deconvolved spectrum, you can, of course, from Fourier go back in the time domain. Someone was asking something? Okay. You can go in the back in the time domain. So in this case, I'm just dividing my reference is the surface recording. And my recording here is the recording inside the borehole. So when I go back in the time domain, generally I observe something like this, where at the top, if I deconvolve it for itself, okay, this is nothing else but the autocorrelation, I will get a pulse, and I will see two pulses inside the borehole, one related to the upgoing propagation of waves, and one related to the downgoing propagation of waves. So I'm able to separate in the time domain whatever is propagating up to what is propagating in the downward direction. Of course, this is in some way disturbing us, also because it's what is generating in the downhole recording some holes in the spectra. And these holes in the spectra are due to the negative interference of the downgoing waves with upgoing waves. When they interfere, they will generate at a certain particular frequency a zero, let's say, in your amplitude at specific frequency. And the frequency at which this will happen will depend on depth, because this depends on the wavelength that is different for different frequencies. So we applied this method working in boreholes in many sites. One of the sites where we work at the beginning was in Istanbul. So in the western part of Istanbul, we drilled together with a Turkish colleague a borehole. In this area around the borehole, we made also shear wave velocity measurements to have information, independent information about the underground structure. And we also installed in different boreholes with different depth. The deepest one was at 150 meters. We also install instruments. So these are the position of the instruments in the borehole. You see around 25, 50, 75, and 145 meters depth. And for the boreholes, we also estimated the shear wave velocity with different methods. The red, blue, and green lines are the shear wave velocities estimated using downhole measurements called PS logging, while the black line were measurements that we have done using simple seismic noise arrays. We will see later in the course how this was done and how it works. So this noise array, they provide in principle this black line that you see it's fitting very well, measurements done considering measurements in the borehole. So why this was important? Because the black line is done using only instruments at the surface and recording some noise signal. This one required that you drill a borehole and you put a tool inside the borehole and you make measurements. So they are much more costly and cannot be repeated in many areas in the town. So here we could show that even simple noise measurements were able to reproduce the results that we could have with more expensive geophysical and geotechnical analysis. So now we knew also the structure of the underground. This was very important to have some control on the experiments. And then we started recording earthquakes. So this is an example where you see just the recordings at different depth inside the borehole. And generally what you notice is that going up close to the surface, the amplitude of shaking is generally increasing, but not at 25 meters depth. We've made several attempts to understand why this is happening. We also thought that could have been related to a malfunctioning of the instruments or a bad coupling of the instruments. The instrument was removed, was checked, was reinstalled. Now, after some analysis, we think that probably this is really related to the underground structure nearby this station, so that is diminishing the amplitude of shaking. In red, I indicate the window signal that we used for calculating the Fourier spectra for the convolution. And by this side, you see the inverse Fourier transform of the results of a spectral ratio, okay? What is really clear is that you can clearly see an upgoing and downgoing wave. And you see also some upgoing and downgoing wave more in the central part. In red, I indicate the theoretical travel time for the shear waves in the boron that we know from the independent geophysical investigation. And you see, the peaks are in good agreement with the theoretical expected position of the arrival of the shear waves. In green, this is the theoretical arrival for the P waves. But you see, the P waves here are not very clear because we are mainly analyzing the horizontal component of motion, which is dominated by the shear waves. The main important result of these studies, of this kind of studies, was to highlight two things that you should keep in mind if you will work with boron. The first one is indicated here to the left. So these are the spectral ratio of a station at the surface at 25 meters, at 50 meters, at 75 meters, with respect to the sensor in the boron at 140 meters, 145. What you observe is that independent on the position of a station, the first peak is always at the same frequency. Now, if my input motion, so if I would be on a good rock side, when I increase the thickness of the sediments, so I'm going from the bottom to the top, I would have expected that the resonance frequency should become smaller, if this is the resonance frequency. But independent of where I am in the boron, that I'm at the surface, 25 meters, 50 meters, 75, the first peak is always at the same frequency. Why this is happening? This is happening because this peak is not due to the amplifications of a wave moving from the bottom to the top, but it's simply due to the fact that the spectrum at different level is divided from the spectrum of the reference. And the spectrum of the reference site in the bottom is not flat, but as a trough, as a hole at exactly this frequency, which is the frequency where I have negative interference between upgoing and downgoing waves. So I have the hole, like you see here, in the spectrum of the basement. So since I have a hole in the denominator, when I take the ratio, doesn't matter if I'm at 75 or at 25 or at the surface, since I have a hole in the denominator, I will have a peak in my spectral ratio. So be careful when you use a standard spectral ratio between the recording at the surface and the recording in the boron, that the peak you are observing, maybe it's not the fundamental resonance frequency of the site. It's only indicating that you have at that frequency negative interference within the boron. So this is putting a big, let's say, alarm, let's say alert on the usage of this spectral ratio. So we can use it if we first remove from the boron recording the effect of a downgoing wave. And this we can do it. We can do it mathematically, and we are able to remove, let's say, the effect of these waves that you clearly observe here. These downgoing waves that you observe here, this pulse propagating down, should be removed to obtain a clear spectrum having in the basement, in the underground, only the effect of this part, of the input part propagating from the bottom up to the surface. So this has to be done if you want to be sure that you will get only the transfer function from the bottom to the surface. Otherwise, you can make some mistake. The other important result of this study that was confirming some of previous results was that if I'm looking at the horizontal component, if I want to have information on the S-wave propagation, doesn't matter if I use a P-waves window or a S-wave window, but it's important that I use the horizontal component of motion. If I want to have information about P-wave propagation, again, doesn't matter if I select a window on the P-waves or a window on the S-waves, but what is important in that case is that I use the vertical component of motion. So from the deconvolution, we can say in this way, P waves can be extracted mainly working on the Z components, on the up-down component of motion. Shear waves can be better extracted independent on the window signal used if we use the horizontal component of motion, okay? So these are some examples of what I was showing before. If you take these recordings, these are just recordings on the horizontal component at different depths. To the left, you can see their spectra. In black, these are the Fourier spectra of this recording. In gray, just for comparison, are the spectra of pre-event noise. Just know if what we observe is signal or is just of an earthquake or is just standard noise. You can immediately already see here some trough in the recordings, also in the spectrum in the bedrock. But okay, if you take this spectra, you calculate the deconvolution and you go back in the time domain. In this case, I think it's very clear the upgoing and downgoing wave effects. And if you take simply the Fourier spectra of this green function, so of the spectral ratio, the effect of a negative interference, you see it's becoming very clear. What is really striking, you see, when you go lower, deeper, the interference is happening at low frequency. When you go to the surface, the interference is going to higher frequencies, okay? So this effect of negative interference has to be taken into account when you are analyzing Borel data for estimating side effects. And generally, why this is important? It's important because one of the tasks that we can have is that we want to make some dynamic analysis of a building. So we need to know what would be the shaking that we can expect happening below a certain structure that we would like to, and we would like to simulate its behavior. So very often we have recordings from boreholes, and we could take this recording from boreholes and we could propagate them up to the structure and simulate its behavior. But we can do this only if we are cleaning this recording from the effect of the downgoing waves. Otherwise, we are simply, again, propagating back the downgoing waves to the building. So this effect of a downgoing wave has to be cleaned by our seismogram before we use them for the upward propagation below a certain building in order to make a correct design of it. This can be done, and this is the large advantage of separating in the time domain upgoing and downgoing wave. In general, what we can do, this is the recorded bottom seismogram where we can see the effect of the upgoing and of the downgoing wave. At the surface, we are generally retrieving something like this. If we make the deconvolution, we will identify the upgoing and downgoing wave in the spectral ratio. So what we can do, we can cancel, let's say, remove the effect of this wave. We only keep this part of the signal. We reconvolve it with a recording at the surface, and we can then, in a very simple way, reconstruct the input motion in the underground without downgoing waves. So you don't have to enter too much into details of this. What is important to know is that if we have these two recordings, even without knowing the velocity structure in between, but simply using this method, we can be able to retrieve the input motion here, simply removing, let's say, the causal part from the deconvolved wave fields that we have obtained from the deconvolution of the recordings at the surface and in the bottom. And this is allowing us to clean the recording at the bottom in order that we can use it then for numerical simulation. So these tools can be really powerful in this sense because they can provide good input motion for numerical simulations of buildings. There are many other things that with this technique that is combining, let's say, frequency and time domain analysis, they can be used to estimate a good velocity from the Borel analysis, but also some information on the damping in the material from the recordings in the Borel and in the top. You can do this also calculating a simple analytical function that is fitting. You see this trough in the spectrum, so you don't remove them, but these troughs are related to the propagation of waves, so are telling us something about the velocity and also the quality factor, so the damping of the material inside, and can be used also in a little bit more complicated inversion procedure, where you can aim at retrieving both the shear wave velocity profile in the underground and the quality factor. So we retrieve, they are simply inverted this. So these are troughs that has been inverted and become peaks. So you see at the end, your model can fit quite well the observation that are in gray with some black line that are the obtained model. However, this usage of Borels, it was proved to be very efficient in obtaining a good velocity structure. You see, these are different models starting from different inversions, but this tool was shown to be much less effective in estimating the damping, the quality factor in the underground. Because even with quite different quality factor, it's still possible to reasonably retrieve the transfer function of the medium. So this is really one of the biggest open questions that we have, I would say, while we are nowadays quite good in retrieving the shear wave velocity below a site, we are definitely less good in retrieving the quality factor that we can then use in numerical simulation of ground motion. This is really one of the main issues that we have at the moment, and many studies are now dedicated to it. Okay, I just skip this moment. Okay, do you have a question for these reference site methods? Was totally unclear or totally clear? Or do you have any questions in between before we proceed? So I assume that it's clear. But if not, maybe think over, we can also ask next time, okay? You have to imagine that this method that I show you on Borel can be used also applied for buildings, for example, to study the propagation in buildings. And it's the classical interferometric approach that you can use also on seismic noise propagation from small to quite large scale, really, national and even global scale. Maybe I come back to this. This is a structure you see where you have sensors in the underground and sensor in a building structure. So with this kind of spectral ratio and interferometry, we can study how waves are affecting buildings, are propagating, how the building shaking then is releasing back the energy in the ground. And this is something that, for example, Anna Maria is studying a lot, because we would like to know if this energy that is released then back from the building is in some way interfering with energy released by other buildings and generating therefore some positive or negative interference that can increase or decrease damage. Okay, I will shortly introduce something that, and then we will go on tomorrow on. So we discuss mainly now the earthquake-based reference site method. And this method was using as a reference the recording, for example, on the outcrop. This means that it requires at least 2 stations, let's say. Or you have seen when we have a network, we can use also quite a large number of stations. Some years ago was proposed also an alternative to use, and the alternative to use only a single station. So different from before, it was introduced what is known as H/V spectral ratio, but in this case for earthquakes. Generally, the H/V spectral ratio is more known especially for seismic noise analysis. So what means for earthquakes? For earthquakes means that we are placing a station here, and we know the station is recording seismic motion in 3 directions. So the 3 components are, for example, north-south, east-west, and the vertical component. So what is the assumption of the method? Just imagine to have also theoretical station in the underground, a little bit like we have seen before. And do not think now to the downgoing wave effect that we have seen before. Only think to the propagation of waves from the bottom to the top. So if we compare the recordings in the underground, and if we compare the horizontal and vertical component recording of the station of the underground, we will see that they have similar amplitude. So if I would calculate the spectrum of the horizontal component and the spectrum of the vertical component, and then I take the ratio, I would see that this is around 1. At least we know it from empirical measurements. So if I assume then that the vertical component of motion is not amplified from the propagation from the bottom to the top, then I can say, okay, the vertical component of motion at the surface is similar to the vertical component of motion in the underground. But since the vertical component of motion here is similar to the horizontal one, I can also say that the vertical component of motion of the surface is similar to the horizontal component of motion in the underground. Therefore, if I take the ratio between the horizontal component at the surface and the vertical component at the surface, it's like, or it's very similar to the ratio between the horizontal component at the surface and the horizontal component in the underground, which is my reference. So from the H over V, if this is true, I should be able to obtain the site response corresponding to the ratio between horizontal to horizontal. And this is on what the method is mainly based on. We will see tomorrow that unfortunately this is not exactly the case, and that while with the H over V we can obtain a reasonable estimate of the resonance frequency of the site, we are not able to obtain a good estimation of the site response, especially in terms of amplification. So I repeat, we have only one station. We take the, you see, it's different from before. These are the recording on the Z and horizontal component at the same station on soil. We calculate the two spectra, and we calculate the spectral ratio for the same station for two different components, the horizontal and the vertical one. Okay? And tomorrow we will go further. Do you have questions about this? This silence scares me. No questions about it? You can imagine what is the advantage with respect to the other methods. The clear advantage is that in this case, we don't need more stations, but even if you are having only a single station, you could make some measurements of site amplification if it would work, or even in areas like we mentioned before, if you have a network of stations, but no station is on a hard rock site, that was a prerequisite of what we have seen before, you could have estimation of site response. But as I mentioned, these are some limitations that we will see tomorrow. Okay? So if there are no other questions, I would stop for today, and then we can continue tomorrow. Okay?
Professor?
Okay.
Yes?
I have a question.
Yes.
Yeah. So when, like, it's not from the last part you were talking about, from the before.
Yeah.
So when we see a down, how to say? So in the signal, we see the downgoing part.
Mm-hmm.
So that gives the peak that you said it's a problem. And I couldn't, like, I lose what you said, the method to correct this problem.
Yeah, in principle, if you remember, when you make the deconvolution, no, so the spectral ratio, but in the complex domain, let's call it in this way, just to make it clear a little bit, I hope. And you go make the anti-Fourier transform. In the time domain, you will see two peaks, no, for the Borel recording. One is corresponding to the upgoing wave, and one is corresponding to the downgoing wave. Okay? If you then remove from this, let's call it transfer function, the causal part, so the part related to the downgoing wave, and you multiply, you convolve, let's say, will be more correct, the spectrum of the surface with this remaining part, without the causal part in the Borel, you will retrieve the recording in the underground without the downgoing wave part. Okay. In reality, we didn't do it with a direct convolution, but with the convolution, you can see, if you are interested, the equation on the slide. But in this way, you can separate, you can separate the part of the wave field which is only related to the upgoing part from the part which is related to the downgoing part. Okay? And this is really your input. If you want to then to propagate something somewhere else, you can say, okay, at 1 kilometer, I know the shear wave velocity from this depth to the surface. Then you can take this input and you can just propagate this up to the surface and then use it also for dynamic simulation of the buildings. Generally, this is done starting from recording at the surface if you know the velocity structure below a site. So you first deconvolve, you obtain this good, let's say, input, and you transport it to somewhere else. But in some cases, the velocity structure below the site, or in many cases, I would say, it's only approximately known. So because you have some other measurements that are telling you what is the structure. And therefore you make a correction that is for a theoretical model.
Mm-hmm.
In this way, you use the real data. So you make an empirical correction, you know? You don't need a model, it's exactly what is recording, independent on the model that you are supposing for the underground. So this could be the advantage. But you have to have the 2 recordings. That's the point, you have to have 2 sensors. Otherwise you cannot do it.
Okay.
Okay?
Yeah, thank you.
Okay, if no other
can
question.
I ask just one question?
Ciao, Chiara.
Now, I was wondering if I'm performing, let's say, a test where the excitation is, let's say, on the surface, like a downhole. I mean, I can have the same problem of the negative interference, but let's say not on the, let's say, in the instrument.
But you mean in the surface recordings?
Yeah,
because you can have a reflection after sometimes. Okay, if this depends how much is long your source. Generally, in downhole measurements, you have a very short duration of your source, so you are able very often to separate what is the input from what is coming back to the surface. In the seismogram, this is much more complicated because you have it's not continuous, but you have a long duration of waves arriving, no, due to the propagation that is not only related to the duration of the source, but you have secondary arrivals due to the heterogeneities in the crust, no? So these waves are continuously arriving later, and these are going to interfere with the downgoing waves that you have later. When you're doing a downhole, generally you have a short duration of your source and then propagation that you can already separate probably in your recording quite well. But in this case, you have an over imposition because the source of earthquakes, okay, it depends on how big is an earthquake, can have a certain duration. But plus there is the whole duration of the wave field, not only due to the direct arrival and first arrival, but to all the other arrivals due to scattering, reflection, and so on in the crust. So you have this continuous overimposition of waves arriving up and waves then generating and then moving down. So it's a little bit more complicated in this field. And in this way, since you are doing the deconvolution, you can simply separate all the effect of the downgoings and of the upgoing waves. But the principle is the same.
Okay.
But if I think to a very short source, it's more or less what you obtain as a seismogram is simply then the response in a simple media. It's already the transfer function. It's the response to your spike, to your simple source. Okay.
Okay. Okay. Thank you.
I hope it was clear enough.
No, very clear. Thank you.
Okay. Thank you.
I also have one curiosity. Sorry
Yes.
if it's a bit late right now. Can I?
Tell me, yeah.
Okay, thank you. I was wondering regarding that part of the ratio of the window, the frequency windows that
Yes.
are selected.
Yeah.
Could it be possible to use sort of time frequency variant Fourier transform and to extract precisely at a particular...
Sorry, I have to go because I have a very important meeting. I will answer tomorrow, promise, okay?
It's fine.
Can you tell me tomorrow? Sorry, I really have to go, but I will answer to you tomorrow morning.
That's
okay?
fine. Okay.
Remember to me the question. Bye-bye.
Bye.
Bye.
Bye, everyone.
Bye.
Bye.
Ciao.